works. And like I've been working on it all afternoon. I went to a whole nother computer to load it. That wouldn't work. I was like, okay, I was about to give up. And then I was like, well, let me just try opening it on different platforms on my phone. And sure enough, it actually showed up on my phone for a change. Usually it doesn't show up on my phone. I was like, oh, but I forgot that I have an update on my phone. So, I guess that's why it's working. So then once I had it on my phone, I was like, okay, I forgot that it might be a little bit of hiccup going from my phone to my tablet, but we were able to work it out. Okay. And let me check here. And yeah, so since we're officially on the stream, stay as a don't connect the audio. That's what I did that. Right there. Okay. Yeah, so again, since we're officially on the stream, I'm just gonna say this one more time. But again, congratulations to Mr. Winston. He did get the top score for this term, for this course. And he's not there by himself. There were like about 3 or 4 gentlemen. There were like a fraction of a points in separation. Sorry for the delay today. It's a bonus lecture. So with today's lecture, like it's kind of like a little bit of application of like all we've been talking about. You're only responsible up through 4.6. And so this is the last section in chapter 4, which is 4.7. It's just like kind of like a filler. You can kind of I just want to kind of expose you to these concepts and ideas. So then I want to say on Sunday, exam 2 becomes available. The spiel there. For the first 7 days, you can earn up to 100%. The due date is basically 7 days later. After the due date, there's like either a 5% or a 10% late penalty. But with all of our assignments, there are limited attempts, and as long as you submit everything with satisfactory scores by the hard deadline, which is that Friday basically at the end of finals week, that Friday at 11:59 p.m. I think it's like May 9th, something like that. That's the hard deadline for all assignments, right? So past that Friday, I think it's May 9th. Let me just pull up my calendar just to confirm real quick. Friday, May 9th is the hard deadline for all assignments, right? So we have pretty much a month, right? Exactly right at a month, right? So again, exam 2 becomes available. Do your best there, and yada yada yada. Okay, so I kind of wanted to just take a look at, I'm more than likely I'm not going to work these out. I just want to kind of touch on some of these notions or ideas. There's a whole adventure to get this up onto my tablet. I guess this is like an older generation tablet, so it won't let me update. You know how I know they can be sued. Apple has been sued for intentionally breaking devices before. This is the second one of my devices that they bricked. I had a laptop, it was nothing wrong with it. It did an update, then it stopped working. Same thing with my tablet now. And I was like, so they're intentionally, it's like these companies it's so frustrating. It's like, because they intentionally do stuff to like slow down your devices. If you have like Windows or HP, then they make their devices susceptible to virus. With Apple devices, you don't have viruses, but after about 5 or so years, they intentionally slow down your device so you can't use them anymore to try to phase them out, to try to force you to get a new device. Like, man, marketing is just like, it makes me want to throw up. Like, it's so like duplicitous. It really is really annoying. Yeah. Okay. So again, this will be our last of new material for chapter 4. Well, you're not responsible for this, so we've finished the last of the material, but this is just the last concept for chapter 4, and numerical integration. So when I'll give my own little summary here. When we introduced integration, we introduced it like with this notion of the Riemann sum. And I don't know if you remember me making a statement like, when you're doing Riemann sum, I know when we first constructed it, we constructed it based on like the left endpoint, right? And so it makes little rectangles, and you kind of draw you extend the rectangle up to where it crosses your curve or whatever. And I think when we introduced it, we did it based on the left endpoint, right? So all the rectangles are based on that left top corner. So what we're going to look at here, we're going to basically explore ways to approximate integrals where we might not be able to take the integral, or there might not be any like formula to integrate. It might just be like loose data. So how can we find the integral based on these different scenarios? And so, long story short, we're going to be revisiting the whole Riemann sum, more specifically, or namely, with the idea of, you know, the left endpoint, based on the left endpoint, right endpoint, or the midpoint. I think there's a trapezoid method, and I think there's a Simpson rule. Simpson rule, I think, is kind of used in like many parabolas. So it's just different ways to approximate the area under the curve for scenarios where you might not be able to find the integral directly, right? So that's what I thought it kind of brings everything together, right? In the past examples, we had cases where we can use a substitution method, or we can use integration by parts, or some other integration technique. So then this is kind of exploring, well, if you can't find the integral exclusively, some ways to still get an approximation for the area under the curve, right? Okay, so let's see, objective here. We like to solve problems using numerical integration methods such as Riemann sums, the midpoint rule, trapezoid rule, and Simpson's rule. Okay, all right, let's keep going. Yeah, why is this? Maybe, I mean, it's fine, I guess. It's showing, so I just need to. I guess I need to be grateful that it's just showing properly, right? So numerical integration is usually used in the following situations: where the antiderivative of the integrand may be difficult or impossible to determine directly, or the data may not conveniently fit into a common function that can be integrated, right? So when we can't find the integral, or we might have data that doesn't fit into a function, then we might try some of these techniques that we're going to explore today. Let me see. So in this example 1, it says Jeff is running on a jogging track. His speed in miles per hour is shown on his belt clip pedometer. Jeff takes 6 readings at 20-second intervals. From this data, determine approximately his distance he has run in those 2 minutes, the 6 20-second intervals. Okay, all right. So we have his speed in miles per hour, and we have his time in 20-second intervals up to 2 minutes. So the distance equals what? Rate times time, d equals RT. So if we say his speed times his time, that'll give us his distance. So then what we'll do is basically construct the rectangle corresponding to each 20-second interval, find the area of each rectangle. That's going to be our speed times our time, length times width, right? That'll give us the distance covered for each of those 20-second intervals, and then add up all those distances. Now his speed is in what? Miles per hour, and the time is in 20 seconds. Miles per hour. So let's convert. We need to get these in the same units, right? So we can convert seconds into what? What do we need? Hours? Let's convert seconds into hours. So that way when we say miles per hour times hours, the unit of hours are going to cancel. We'll be left with miles. So let's convert. So instead of looking at it as 20-second intervals, we're going to convert that into hours, right? So how much of an hour, right? So let's do the conversion. So for instance, if we consider 20 seconds, right? I'm going to put it over 1. We want to convert this to hours, so we're going to say times. We can go what? 60 seconds is what? 1 minute. So we can say 1 minute corresponds to 60 seconds. Okay. And then what? 60 minutes is an hour. So 1 hour corresponds to 60 minutes. So when we're doing our conversions, if you're not aware of this already, when you have like 1 unit on top, that same unit needs to be on bottom in the next portion or the next factor so that the units cancel, right? The units of seconds are going to cancel. The units of minutes are going to cancel. And we'll be left with our desired unit of hours, right? So we're going to say 20 divided by what? 3,600? Hey, Google, what's 20 divided by 3,600?
20 divided by 3,600 is approximately 0.01.
0.011, is that right? 1 over 100? 100th of an hour, is that right? Why didn't that feel right? here. 20 seconds, 60 seconds in a minute, 60 minutes in an hour. Let me just check. I think it's right, but I don't know why it feels wrong. This is exactly what I want. Okay, let me clear. So if I said 20 divided by 3,600. Oh, I know why. No, I don't know. Let's see. Okay, well, maybe she said 2. What? Yeah, I was like, something she was doing it just didn't sit right in my stomach. I was like, this don't. Oh, she rounded. That's why she said 0.01. She rounded. Okay, that's why I was like, yeah, that wasn't the number I was anticipating. 1/180 is what I'm going to go with. I was like, why am I getting something weird? Okay, so 1/180th of an hour, right? So each time interval is 1/180 hours, right? I guess I could do a rough sketch. I mean, it's not too bad, sure. Let's go like this. And I think I can fit it in this way. Well, I probably shouldn't, but I think I am. Now, what I could do, let me move this. How do I want to do it? Trying to create some space for myself. I'll duplicate this. And then what I'll do, let me pull a copy. What slide is this? So that's slide 6. I'll copy. And I'll paste it right there. Paste. And I'll just give myself some space. I'll delete this file. Okay, that's fine. Okay. And let's cut this. I'll paste it here. I need a copy of the chart. Okay. Let's go like this. Copy, paste. And we said each of these was 1/180th of an hour. Right, and like that's why you kind of have to be careful about just like using calculators and like some of these devices just blindly. Because I was like, she said 0.01. If I had written 0.01, it would have thrown everything off. And I was like, for whatever reason, it just wasn't sitting right in my stomach. So I was like, well, let me just check another source. And then, I realized that she had rounded, and that's what was throwing things off. I don't want to spend too much time doing this. 20 seconds. Let me see. Let me see. 1, 2, 3, 4, 5, 6. So I'll go 1, 2, 3, 4, 5, 6. We need to go maybe to 20. 2, 4, 6, 8, 10, 12, 14. Down, so 14, 16, 18, 20. So about like here. Let's see. 16, 18, 20. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Okay, that's fine. All right. So then here, I'll do this one as we'll do this as our time. So we'll call this T, and then we'll do our speed. We'll just call it S. Do you guys ever watch iShowSpeed? I'm just curious. His life is interesting. Like he's an interesting person. It just seems like a dream to just get paid to have fun and go on adventures. All that. I was like, man, that seems like a lot of fun. I ain't gonna lie. we'll do this. We'll still put 20 seconds here, but we're just aware that that's 180th of an hour. We'll go 20, 40, 60, 80, 100, and then 120. And then this is our speed in like miles per hour. These are in seconds. All right, so just to be aware. 20 miles, so let's see. 2, 4, 6, 8, 10, 12, 14, 16, 18, and 20. Go this color. So for that first one, right, his speed at the 20-second was what? 15 miles per hour. So, and let's do. Sorry. There it is. I want this one. Okay. I mean, not really errors. It's just things that are thrown off my rhythm. But it's like it's okay. I mean, 1 or 2 bad days out of however many we meet isn't bad. I don't too bad about that. I just I don't like to waste you guys' time. Okay, so at the 20-second mark, he did 15 miles per hour, which is right here, right? And then at 40, he was at 17. I wonder if he slows down right here. 60, he was at 18. Is he speeding up? Nope, that's not right. 60 is 18. At 80, it is off. Hang on. 40. There we go. I see my error. These two. All right, that's better. Okay. And then at 80, he was at 12. Okay, he finally slowed down. It's like, these numbers aren't realistic. He should slow down. Maybe. 80. At 100, he's at 14. 14. Okay, right there. And then at 120, he was at 10. So 10 was like this here. Okay. And then so what we can do is make rectangles based on that data. All right. That's fine. I'll come back. All right. Here's the first one. I just want to duplicate this. The next one kind of goes up to there. Duplicate. There. So this is kind of similar to like what we did initially. If we can get to the topics, there are some other applications though, like some other conclusions that come out if we can get to them. And I'm gonna do one other thing right here. This color. Let's do that again. Okay, about like that. Let's go style. That can be thin, fill with that one, and duplicate. And duplicate. That's good. And duplicate. Okay, and duplicate. Okay, I think we're starting to get into the flow now. Duplicate. Here. Okay. All right. So we have these rectangles, and so then based on this data, so then we can find the distance traveled. If you say the distance, the rate times the time. So if we said his speed, the 15, like for that first 20-second interval, if we said 15 times the 1 over 180, that'll give us his distance, right? So let me, is that going to show up this time? Of course not. Okay. Okay, so let's see. I'll just write it here, I guess. Long story short, it's going to be what? I mean, that's fine. Well, can we do that? Because if it's 15 times the 1 over 180, it's going now, whatever it was. Ugh. Okay. All right. So let me see. If we say the 15, because if we're saying 15 times 1 over 180 plus 17 times 1 over 180, I think we can just factor out the 1 over 180, add up those numbers and then just multiply it by 1 over 180, and I think we'll be okay. Let me see. 10, 20, they're all 10s. So then, what is it? 60. That's a 12. That's 20, 22, 26. 26 plus 60, 26, 86. I think it's 86 divided by 180. Let's see. I think that should work. So 86 divided by 180 miles. So almost half a mile, right? I think that's actually correct. I think a spider landed on me. I didn't know what it was, and I smashed it. And I was like, "What is this?" And then as I kept wiping it, I was like, "Oh, that was a spider." I was like, "Ugh." It saved my life though, because spiders, you gotta be careful. But it's gone now. So it just was in the wrong place at the wrong time. Yeah, I think this is good actually. 0.47 miles, right? I guess I'll write it here just for reference so you know that it's there. Well, it's on the next slide, but we got 0.47 bar miles was the distance he traveled. Okay. So all we did was find the area of each rectangle and then add up the areas, right? We just did the 15 times the 1 over the 180 plus 17 times 1 over 180, but I used a little bit of algebra. I added those numbers up. I factored out the 1 over 180, yada, yada, yada. Okay, so we got it here. So I think that's actually correct. All right. So, and then if we look at our prepare notes, we start by plotting the data, right, like we did. And then rectangular bars are drawn with each height, with the height of one data point, right? So I think we got that same idea. Then we found the hour. We converted from seconds to hours, right? So each bar is 1/180th of an hour wide. So we captured that. And then so you have this chart, which is essentially what we did. The 1 over 180 times 15, we get an answer. Plus 1 over 180 times 17, we get an answer. And then you add up those results, and they got the same thing that we got. So in the 2 minutes, he ran approximately half a mile. That's really fast. I know that like a goal for many people is like I think it's like is it a 4-minute mile? Yeah, I think it's a 4-minute mile. 10-minute mile, I don't think it's that impressive. I think it's 4 minutes. Because like usually when I'm on foot, a mile, I average about 20 minutes a mile. It's just a leisure pace. Like walking leisure is about 20 minutes a mile. So, I know some people try to go for like the 4-minute mile. That's like one of those checkpoints or whatever. But anyway, so again, we had this data. We were able to use integration using basically the Riemann sums, right? Okay, let's see what else we can go with this. So the Riemann sum, just to kind of revisit, suppose we want to approximate the value of the integral as x goes from a to b of f of x dx. We subdivide the integral from a to b into n equal size subintervals. Let these n subintervals be given by, you have your left endpoint a up to x1, and then x1 to x2, and then x2 to x3, and then the last x1 until you get to b. Each subinterval has a width of delta x is going to be b minus a divided by n, right? So that's the width of each subinterval. Your right endpoint minus your left endpoint divided by the number of subintervals, and that gives you the width of each subinterval. Okay. So then rectangles are erected over each subinterval, and then we have a choice in that we can define the height of each subinterval as the function value of the left endpoint of each endpoint. So then the heights would be like the height of the first subinterval will be based on what? A, and then x1, x2, and then up to xn. The area of each rectangle is the width multiplied by the heights. Therefore, the total area under these rectangles in which we use the left endpoint to define the height is given by this. So the area based on the left endpoint, delta x times f of a plus delta x times f of x1, right? These are all based on the left endpoint, okay? So then not only do we have the option to do it based on the left endpoint, we can construct these rectangles based on the right endpoint as well. If we use the right endpoint of each subinterval, then the function values, instead of starting with a, which is the leftmost endpoint, now we're going to start with x1, right? So if we think about that first subinterval that goes from a to x1, if we're doing it based on the right endpoints like we just did in our previous example, the first height is going to be based on x1, like we just did one like that, all right? And their sums based on the right endpoint is going to be delta x times f of x1. This one goes up to b. Right? Often the average of these figures is calculated to give a better approximation. So, in the example that we just did with the speed based on the 20-second intervals, you can see where those rectangles are constructed with the right endpoint. So we could have constructed it based on the left. We will get a slightly different answer. So then, if you have the area based on the left endpoints and the areas based on the right endpoints, you can take the average of those. What we usually do though is like take the average of the interval, right? So if it goes from 0 to 20, we might say, okay, well, if we can get the data at 10 seconds, then we will use that. I think in the previous example we didn't have really a choice, but instead of using the 20 or the 0, we can use the average. In that case, would be the 10-second interval. Then the next one will be 15, and then 25, right? The midpoint of each of those segments, right? So that's kind of what we're going to be exploring here. Okay. I kind of left my notes here, but that's okay. So here we're asked to find the approximate value of this integral using 6 equal size subintervals. Okay. So if we're integrating as x goes from 0 to 3 and we want 6 equal size subintervals, then the width of each subinterval is going to be what? 3 minus 0 divided by 6, which is a half, right? So every half of a unit, that's going to be the width of each subinterval, right? So we have that there. Okay. So, and again, it said approximate. So what we can do, I'm just going to do kind of a rough sketch. I'm not going to go into like full details, copy and paste. All right. So let's see. I'm just trying to think of how to construct it. The left, right? So if we do it based on the left, okay, I'm thinking the table. Okay, I'll just do something like this. So 0, right? So if we start at 0, and then what the next one is, what, a half, and then 1, and then 1.5, and then what, 2, and then 2.5. Now, if we're doing this based on the left, 1, 2, 3, 4, 5, 6, okay? So these are like the subintervals. All right. And then the height, I'll just call it the height of each rectangle. So we would basically plug this in. So we would say like f of 0, we get an answer. F of 0.5, we get an answer, right? I think we'll just use our calculator. Okay, so what I'll do is I'll go to my y equals, and I'm going to put the square root e to the power of x plus 1. I think that's good. Approximate the value. So give us the area under the curve. Okay, yeah. So I'll let that be my f of x, right? And then let's evaluate. For instance, actually we can pull it up in the table. If I go to table set, I wanted to start at 0 and change by 0.5, and then go to my table. Okay, I'll use these approximations, right? Just need a little bit of space. So for instance, this one, I'll write 1.4142, and then 6275. Okay. 9283. Okay. Oh, of course. I'm thinking, I'm automatically thinking they're 1. That's right when they jump up. 3413. 8964. Again, these are approximations. 5919. Okay. So then the width of each one is a half. So then we basically just add up those numbers and then times a half, and I think we'll be good to go. Right? Now I think this can do summation as well. So let me see if I can get that to work. If I go to math, I see my derivative, solver, absolute value, max, min. I think that's it. Where else would it be? Stat, calculate? No. There's another place. Maybe test? No, that's not it. Variables. Let me try variables. No, I don't think that's it. Math, and I think I tried all these. I think it does have some. I just got to think about absolute value and max, min, probability. Where else? Apps, angle. Let's see, is it here? No. List, sort, sequence, sum. That might work. Math. There it is. Okay. So I think what I did, I went to list. If I hit second stat and then over the math, because I was like, I know it's math. Okay, so we want the sum. I think of that function that we just did, right? As x goes from that's going to do it in increments of 1 though. How can we capture this? Is it x over 2? So like for instance, when x is 1, or when x is 0, we get 0. When x is 1, we get a half. I think we need to do, hopefully this works, x over 2. So the sum of that function as x over 2 goes from 0. Let me see. 4 over 2, 5 over 2, 0 to 5. Let's see if this works. And we're going to get some, and whatever answer we get, we want to say times 0.5. I'm being a little bit extra. You don't have to do this. You could just add up those numbers and then multiply by 0.5. I was just trying to see if I can get the summation to work. Let me see if I do steps of 1. Okay, what's the time? Oh, we are out of time. Man, I know how to eat up time. Okay, let me I want to check something real quick because we're so close. How to do a summation on TI 83 plus. That's that one, I think. Some, I just need to see one, show more. Can I do a sum of a function? Okay, sequence. That's what I'm missing. As x goes from. Okay. So I just need that sequence term. That's what I was missing. Okay, so the sum right here. Insert. If I go back to stat sequence. There it is, number 5. Okay. Let me get rid of this extra thing here. And we need one more parentheses. Let's see, cross our fingers. Darn it. Okay, another thing that I could do. Instead of trying to do that function. Okay. I'll insert square root. I'll just type the function in here. I was trying to call it, but for whatever reason I couldn't get it to work. I see the time. I'm about to get you guys out of here shortly. E to the x plus 1, close the square root. Let's get rid of that. I'm sure that works. I'm just not typing something right. As x, and it's probably the x over 2 that's throwing everything off. But that's what I really need. Darn it. Okay. Only thing is that it's because it's in half intervals. I hadn't figured out how to capture that just yet. Oh no, that's not gonna work. Okay, I think I know what I can do. I'm gonna do this. I'm gonna go like get rid of that. And then maybe if I insert the 1/2 here, it'll work. Let's just see what happens. Okay, we got an answer. And we got it times the 0.5. I want to see if that's correct. Each subinterval has this width, right? So again, all we're doing is adding up those numbers and saying times 0.5. Oh, it worked. 6.9. I knew it was close. Right? Okay. We got a solid 10 minutes. I'm going to take advantage of the 10 minutes, right? So we got our result. And what you see in that chart is essentially what I was doing. Like I said, I was just trying to use my summation notation. And we figured out how to capture the 1/2 because it was the subintervals were based on a half instead of 1. So, we were able to get that going. You don't necessarily, again, you don't have to do it the way that I did it. You don't have to do it at all. I'm just, as long as you can get the concept there. And, and again, this is just for your own growth. So if we did it based on the left endpoint, we get this result. I think we might be able to quickly do it based on the right. Now, if we did it based on the right endpoint, instead of starting at 0, it's the first height is going to be based on the 0.5 and it's going to go up to 3, right? So let me see. To capture that here, the width is still the 1/2. The function is the same. The x over 2 is good. I think the only thing that changes are the indices. Instead of starting at 0, I think we go from 1 to 6. I think that's the only change we need to make to get that right endpoint. So I'm going to change this to a 1 and to a 6. And let's see. We should get 8.5 something. God is good. Look at that. Just a click of a button, change 2 little parameters, and we do it in an instant. Come on now. That's exciting. Like, how can you not be excited about that? So all that work, and so it's like the hardest part was just figuring out how to, get it into your device. But then, with the click of a button, we process the whole thing. And this is just using a TI-83. You can easily do this also in like a number spreadsheet, Excel spreadsheet. So if you're working on an iOS device, numbers is included. Honestly, as a student, as long as you have access to your Morehouse email, which you should be able to keep open even after you graduate, you can use the Microsoft Suite. As long as you have access to your student email, you can use the Microsoft Suite till Kingdom Come. Most schools, that's usually how that goes. So So we have the area based. If we did it based on the left endpoint, we have the area based on the right endpoint, right? And that was smooth. Come on now, just changing two little parameters, and we automatically got the other. Now that's exciting. Anyway, anyway, okay. So again, we were able to find the area based on the left endpoint. We were able to find the area based on the right endpoint. So then, for a better approximation, we might try to use the midpoint, halfway between the left and the right. So given some closed interval AB subdivided into n equally sized subintervals, where the width of each subinterval, or our delta x, is going to be b minus a over n. The approximate value of this integral is given by the midpoint of each subinterval, where that's going to be the area based on the midpoint is your delta x. See, here they factored out the delta x. And to find the midpoint, the height based on the midpoint, they, like for instance, that first subinterval, they took the a plus the x1 divided by 2. So they basically took the average of the endpoints of each subinterval to get the middle, right? And so the height is based on the middle of each subinterval. Okay, I think we're going to find a way. Now, let me see. If we wanted to do the last one with something similar, let me think about it. I got to think now. The right endpoint, left endpoint. How could we capture that? Because we want the average. I got to think about this one. We were able to capture we could just take the average of our answers. We could say we should be able to do like that first answer, just basically take the average of these two answers. Okay, what I'll do is I'm going to store this as alpha A, and then I'm going to recall the other one that we did, this one, okay? And then I want to say parentheses, I want to say that answer plus alpha A divided by 2. I think this will work, right? And then we should get something, right? So that's about halfway. Let's see if that worked. Let's see if that worked. Now, if we wanted to use the midpoint rule, right? The height, those x values, you had to find the midpoint of each one, right? Let me think. That's the 0.5. Okay. The average of each subinterval. 0 plus 1 over 2. Okay. Anyway, I'm trying to think of how to get that in the formula, but I'm not going to worry about that. That's been a little bit extra. Okay, we got it here. 7.67, I think is what we got. Oh, no, we didn't. 7.67, so maybe not. So it's close, but what's better is to just actually write it out. I'm still trying to think of how to capture that like we did with the left and the right. I'd have to think about it a little bit more to see if I can get it to work. And I'm kind of pressed for time. I don't want to keep it more than about 2 minutes. But I feel like you should be able to kind of follow this, right? The first subinterval goes from 0 to 0.5. So then the x value is going to be based on the average, which is just 0.25. Right? And so you basically find the average of each subinterval to get the middle, and then you do the height based on that, and then it's kind of a repeat from there. Okay, so these are the heights based on the midpoint. And so what it is like if you look at the curve, on the left side of the endpoint, you got a little bit that's above, and then on the right you have a little bit that's below. So then it kind of like evens out a little bit, and so that's why it's a slightly better approximation. Okay. So then, and just to kind of like scan over this, so we have the trapezoid rule. The trapezoid rule, you're basically creating a trapezoid. So consider the closed interval AB divided into n equally sized subintervals. The approximate value of the integral is given by the trapezoid rule, which is going to be the area under the curve based on the trapezoid, based on this formula, right? So f of a over 2, and then the height for x1, x2, up to n. Let me see. Yeah. Right, so in the previous example, we had rectangles. We did it based on the left endpoint of the rectangle, the right endpoint of the rectangle, and the midpoint of the rectangle. But the rectangle had parts that were like above and below, so it's a little bit off. The smaller our rectangles, the better our approximation. So what this is, these are trying to do shapes that are a better fit for our curve. Let me see. I don't know if we get an image here, but you know, the formula's here. Okay, so from the previous example, f of 0, right? So this is basically using the formula directly. And again, the idea here is that what it's doing is creating a trapezoid that's like a better fit. It's a closer fit. Like if you think about, instead of using rectangles, you're going to use like a trapezoid. It's probably be rectangular on the bottom and then slanted on the top, and it'll give us a better approximation for each subinterval. All right, and so you would use this formula. Okay. So that's the trapezoid rule, just a little introduction. And then we have Simpson's rule. I think Simpson's rule, what it's doing is like the shape that it's kind of piggybacking off of is like a parabola. So like mini curves. Consider the closed interval AB be subdivided into n equally sized subintervals, where the width of each subinterval is b minus a over n. Here, n is an even number, right? N needs to be an even number. The approximate value of the area under the curve, or the integral, is given by our Simpson's rule, where it's going to be the area under the curve, b minus a over 3n, basically using this formula. You got that left end point a, 4 times the height from x1 plus 2. I think it alternates with 4 and 2 until you get to the end. The last one is the height of b. Again, I'm under the impression that the Simpsons rule, I'd have to dig a little bit more for Simpsons rule, but I think the basic shape is like a parabola. I think that's what they're using. Matter of fact, I think we have it over here. I see the time. Simpsons rule is just using a formula there. I'm just going to have to leave that because we're out of time. I want to kind of review this real quick. So with our section summary, the process of numerically approximating the value of an integral using geometry is called numerical integration. We subdivide the closed interval AB into n equally sized subintervals. Let these n subintervals be given by this, and then each subinterval has a width of b minus a over n, right? So we then use any of the following techniques. So the Riemann sums is basically the rectangles where we can do it based on the left endpoint, based on the right endpoint, right? We explored several examples there. We can also do it based on the midpoint rule. I know we kind of had to breeze over that a little bit because we're out of time, but you can do the Riemann sums based on the midpoint rule, right? So these are different ways to calculate it. The trapezoid rule, so trapezoids are drawn over each subinterval. The sum of the area of all the trapezoids is denoted here, right? So again, the trapezoid rule is using trapezoids where, what is it? Is that right? Anyways, it's using trapezoids over each subinterval. I'll leave it at that. That's what I'm comfortable saying. There's a little bit more I want to say there, but I don't want to go deeper. So I'll leave it there for now. And then with Simpson's rule, the closed interval AB is divided into n subintervals where n is even. The graph of f is approximated by n over 2 parabolas. All right, that's what I was trying to get to. It's approximated by n over 2 parabolas. And then the area under f is approximated by Sn, right, given by this, right? So that shape with Simpson's rule is based on parabolas, right? So we've seen it with rectangles, trapezoids, and parabolas. Okay, and again, so the takeaway from today, again, you don't really need to commit this to memory. This was just a bonus lecture. I thought it was something fun. It was fun for me. I glanced at it in advance, but this is my first time looking at it. But then it's an application of stuff that we've been talking about. So it's like, that's why I thought it'd be fun to look at. You're not like directly responsible for this, but this is just like a culmination of all the stuff that we've been talking about. And again, these are some techniques that you might try when, if you ever find yourself in a proctored testing environment or whatever, and you need an integral, and for whatever reason you cannot exclusively find the integral, you can't calculate it or nothing is working, you might try one of these techniques to get an approximation, right? So this is just something that like you can add to your bag of tricks or your repertoire. Are there any burning questions before we go our separate ways? You guys are awesome. Are there any burning questions, right? So again, to kind of recap, that's pretty much it as far as new material for the semester. Again, exam 2 should become available this Sunday. Probably next week we'll devote to reviewing for exam 2. which is chapters 3 and 4, minus section 4.7. And then after next week, I think we have 4 sessions remaining where we're going to be meeting. And basically, we're going to use that time to review for the final, to prepare for the final. So if we have 4 sessions remaining, each session is going to be devoted to a chapter. So like chapter 1 is one session, chapter 2 is another session, chapter 3 is a session, and then chapter 4 is a session. Okay, guys, if there aren't any burning questions, thank you for your patience. Again, you guys are awesome. You know, we didn't come this far to just come this far. So do your best to try to finish. Honestly, at this moment in time, anybody can still get whatever grade they want. Anything is still possible. Collaborate. It's okay. Just do what you need to do to kind of get it submitted. If there aren't any burning questions, we're going to go ahead and end the session here. And now from one beautiful mind to another, take care, gentlemen. Have a great weekend, and we'll meet back on Monday to review for exam 2. All right, guys, take care. Peace. That was interesting. It's the weekend. Party time. Let's go. Man, I know how to keep myself distracted, I tell you. All right, guys. All right, take care. Stop broadcasting. Come on. Let me check the chat. Chat looks good. All right, guys.